Dear viewers, welcome to Finite Element Analysis. In this video, we are going to see the fundamental formula of heat transfer problem. In this video, we are going to see the thermal problems, one-dimensional element stiffness matrix, force vector, how to calculate the heat flow. The figure shows the one-dimensional heat conduction problem examples. Heat conduction in a thin long rod, the heat flow will be high end to lower end in one direction only. Then another example, a furnace wall with the dimension in x and y z direction much greater than the thickness in the x direction. Composite wall, example of heat transfer problem. Actually, in one-dimensional problem, the following stiffness matrix will be formulated based on the Fourier's law and shape function. Based on the heat transfer mode, there are three types of heat transfer mode. One is radiation, conduction, and convection. Then based on the shape function and Fourier's law, we formulate the axial conduction. The axial conduction formula is Ka divided by L. K will be indicate the thermal conductivity. A will be indicate the area of the cross section of the element. L is the length of the element. Then based on the nodal points 1 minus 1 minus 1 1. Then perimeter convection is based on the heat transfer mode. The perimeter convection is convection coefficient H, perimeter of the element P, L is length of the element divided by 6 to 1 1 2. The end convection at node J based on the heat transfer of the element. So that at node J means, so 2 cross 2 matrix, the convection coefficient and area of the element. In this slide, the force vector may be consist of perimeter convection, end convection at node J based on the element heat transfer mode. The perimeter convection is convection coefficient H, perimeter P, length of the element L. Then Tf will be indicate the temperature of the surrounding fluid. Divided by 2, 1 1 will be indicate the nodal points I and J. The end convection at node J only is that one of the end will be exposed to the node J will be exposed to surrounding. That's why that nodal point J only the value of coefficient value, convection coefficient and area of the element and temperature of fluid is coming. Then another I node will be 0. The example of force vector seeing in this slide, it is a rectangular cross-sectional pin. It is one end is connected with 330 degrees Celsius. Then surrounding fluid TF is 30 degree. Actually, the heat transfer will be flow in one direction only, x direction only. So for this rectangular pin, that I node is connected exposed to surrounding fluid. So we can use this force vector formula, end convection at node J. We can use this formula. Next, in this slide, how to calculate the internal heat flow. The heat flow is found from Q flux equal to minus K, then interpolation function P and vector of temperature distribution. For one-dimensional element with a linear interpolation function P equal to 1 divided by L minus 1 1. The heat flux, how we can validate? By using a external temperature measuring sensor, we can measure the surface temperature sensor measuring T1 and T2. We can validate our hand calculation result. The diagram shows the thermal heat loss and gain through material heat flux Q. That K will be indicate the thermal insulation of the thermal conductivity. So T1 is inside the temperature, T2 is outside temperature. Then T1 and another T2 will be indicate the surface temperature sensor measuring and surface sensor measuring 2. Heat flux can be determined using two surface temperature measurement on either side of the material using temperature sensor if K and X of the material are also known. The diagram indicate heat flux through a thermal insulation material with thermal conductivity K and thickness. Thank you for watching my video. I will see you in next video.